What if everything you know about the beginning is wrong? Right now, as you're watching this, you exist because of the most impossible event in cosmic history. 14 billion years ago, every atom in your body, every star in the sky, every galaxy we can see, all exploded from a point smaller than the period at the end of this sentence. Scientists called it the Big Bang, the beginning of everything. But they were wrong. The Big Bang might not be the beginning at all. It might just be the latest episode in a cosmic story so mind-bending that it will shatter everything you thought you knew about existence itself. We're about to explore colliding dimensions that birth universes, black holes that contain entire realities, and quantum loops that make time itself bounce backwards. We'll discover how consciousness might be creating reality, how our universe could be a hologram, and why everything might be pure mathematics. If you are ready to discover what really came before everything, hit that like button and subscribe to Stellify Science, because this journey will change how you see existence itself. What you're about to learn will keep you awake at night. Prepare yourselves. We begin. The singularity problem that broke physics. Picture this. You're trying to divide by 0 on a calculator and it just says error. That's exactly what happens when physicists try to understand the very first moment of the Big Bang. We call it the singularity problem, and it's been driving scientists crazy for decades. According to our best theories, if you rewind the universe like a movie playing backwards, everything gets smaller and smaller until it reaches a point of infinite density and infinite temperature. That's the singularity. But here's the thing that keeps physicists awake at night. Infinite anything in physics usually means your math has broken down completely. Think of it like trying to cram every person on Earth into a space the size of a pinhead. It doesn't work. The laws of physics we know and love simply stop making sense when you reach these extreme conditions. Einstein's general relativity, which beautifully describes gravity, space, and time, starts throwing up its hands and saying, "I quit." What makes this even more mind-bending is that this isn't just about the beginning of matter and energy. This is about the beginning of space itself. Before the singularity, there wasn't even emptiness. There was literally nothing for anything to exist in. No up, no down, no here, no there. The temperature at this moment would have been 10 million trillion degrees. That's hot enough to make the core of the sun look like an ice cube. At these temperatures, not only would atoms not exist, but even the fundamental particles that make up atoms would be torn apart into pure energy. But here's where reality gets stranger than science fiction. If the singularity actually happened the way our equations suggest, then asking what came before it is like asking what's north of the North Pole. The question itself might not make sense because time itself supposedly began at that moment. This is why brilliant minds have been working overtime to find alternatives. Maybe the universe didn't actually reach infinite density. Maybe something else was happening that our current theories can't capture. Maybe the Big Bang wasn't really the beginning at all, but just a transition from something that came before. Recent discoveries are pointing toward exactly that possibility. Advanced telescopes are picking up patterns in the cosmic microwave background radiation that suggest the universe might have had a complex history before the Big Bang. These aren't just theoretical ideas anymore. We're starting to see actual evidence. The singularity problem isn't just a mathematical headache. It's a doorway, and scientists are finally figuring out how to walk through it. But to understand what might have come before, we need to dive into the strangest realm of physics, where space and time themselves become choppy and uncertain. The quantum foam, where reality becomes impossible. Welcome to the smallest possible scale of reality, where everything you think you know about space and time falls apart. At distances smaller than 10 to the negative 35th power meters, space isn't smooth like we imagine. It's bubbling and churning like a pot of boiling water. Scientists call this the quantum foam, and it's where the rules of everyday reality go completely haywire. Imagine zooming into the surface of a calm lake. From far away, it looks perfectly flat. Get closer, and you see gentle waves. Closer still, and you notice tiny ripples. But keep zooming in to the molecular level, and suddenly the smooth surface becomes a chaotic dance of individual water molecules bouncing around frantically. That's what happens when you zoom into the fabric of space itself. At the quantum foam level, pairs of particles spontaneously pop into existence and then annihilate each other in less than 10 to the power of negative 43 seconds. That's so fast that light, the fastest thing in the universe, can only travel about 10 to the negative 35th power meters in that time. We're talking about distances so small that if you enlarged an atom to the size of the solar system, the quantum foam would still be smaller than a grain of sand. This isn't science fiction speculation. We've actually measured this foam indirectly through something called the Casimir effect. When you put two metal plates incredibly close together in a vacuum, they get pushed together by the quantum foam itself. It's as if space is constantly creating and destroying tiny amounts of energy, and we can detect the pressure it creates. The Casimir effect has been measured in laboratories around the world, confirming that the quantum vacuum is not empty, but filled with fluctuating energy fields. These experiments show that space itself has an intrinsic structure at the smallest scales. Scientists have even used the Casimir effect to power tiny mechanical devices, extracting energy directly from the quantum vacuum. While the amount of energy is minuscule, it proves that the quantum foam is real and measurable. But here's the mind-blowing part. This quantum foam existed before the Big Bang, while everything else about our universe supposedly began 13.8 billion years ago. The quantum foam has been there all along, bubbling away in the deepest foundation of reality. Scientists think this foam might hold the key to understanding what triggered the Big Bang. Maybe our universe emerged from a particularly large fluctuation in this quantum sea. Think of it like a soap bubble forming in a bathtub full of foam, except the bubble became an entire cosmos. The mathematics suggests that in the quantum foam, time itself becomes uncertain. Past and future can get mixed up. Cause and effect break down. Events can happen before their causes. It's a realm where the normal flow of time that we experience every day simply doesn't apply. This means that whatever came before the Big Bang might not have happened before it, in any way we can understand. The quantum foam exists outside of time as we know it, in a realm where before and after are meaningless concepts. Recent theoretical work suggests that the quantum foam might be structured in ways we're only beginning to understand. Different regions of the foam might have different properties, creating a landscape of possible universes with varying physical laws. Some areas of the quantum foam might be more conducive to universe formation than others. The Big Bang might have occurred in one of these fertile regions, where the conditions were just right for a stable, expanding cosmos to emerge. The cosmic inflation mystery. But if the universe emerged from quantum fluctuations, something had to trigger the massive expansion we call cosmic inflation. Something extraordinary happened in the first tiny fraction of a second after the Big Bang. The universe expanded faster than the speed of light itself. This cosmic inflation solved many puzzles about why our universe looks the way it does today. But it created an even bigger mystery. What could possibly have triggered such explosive expansion? The answer might lie in a hidden phase of cosmic evolution that happened before our Big Bang even began. Picture a balloon being inflated, but instead of growing steadily, it suddenly explodes from the size of a marble to the size of a basketball, in less time than it takes light to cross a single atom. That's what cosmic inflation did to space itself. In just 10 to the negative 36 power seconds, a region smaller than a proton expanded to the size of a grapefruit. This isn't just fast expansion. This is space itself stretching so rapidly that 2 points that were close enough to touch became separated by millions of miles instantly. The expansion was so violent that it would have torn apart any matter that existed, leaving only the pure energy that would later cool and condense into the first particles. But here's what puzzles scientists. Inflation requires a special kind of energy field called the inflaton field. This field had to be perfectly balanced on a cosmic tightrope. Too little energy and inflation never starts. Too much and it never stops. The conditions had to be just right, like balancing a pencil on its tip. What could have set up these precise conditions? Recent theories suggest that our inflationary period might have been just one episode in a much longer cosmic drama. Before our inflation began, space might have been going through cycles of expansion and contraction, each cycle fine-tuning the conditions until inflation finally triggered. Think of it like a mountain climber who has to traverse multiple peaks before reaching the summit. Each peak represents a different phase of cosmic evolution, and our Big Bang inflation was just the final summit in a long journey that started much earlier. Advanced computer simulations show that these pre-inflationary phases could have lasted for incredible amounts of time. We're talking about epochs that make the 13.8 billion year age of our universe look like a brief moment. During these phases, space could have been experimenting with different configurations, different energy densities, different physical laws. The inflaton field itself might have evolved through multiple configurations before settling into the state that produced our universe. Each failed attempt at inflation might have created small, unstable regions that quickly collapsed back into the quantum foam. Only when the field reached exactly the right configuration did inflation succeed in creating a large, stable universe like ours. The most exciting part is that some of these pre-inflationary conditions might have left signatures that we can actually detect. Gravitational waves from these ancient epochs could still be rippling through space today, carrying information about cosmic events that happened before our universe even began inflating. Scientists are building increasingly sensitive detectors to search for these primordial gravitational waves. If they find them, it would be like discovering a message in a bottle from before the beginning of time. The next generation of gravitational wave observatories will be sensitive enough to detect these ancient signals. Space-based interferometers with laser arms, millions of miles long, will listen for the whispers of cosmic events that predate our Big Bang. But cosmic inflation might be just one way that universes can begin. Some theories suggest that the Big Bang was actually the end result of a cosmic collision that had been building for eons. The Big Bounce theory: death is just rebirth. What if the Big Bang wasn't a beginning, but a bounce? Scientists are discovering that our universe might be caught in an eternal cycle of expansion and contraction, where each Big Bang is actually the rebound from a previous cosmic collapse. Imagine a cosmic heartbeat that's been pulsing for eternity. Our universe expands for billions of years, reaches a maximum size, then starts contracting back down until it squeezes into an incredibly dense state. But instead of collapsing into a singularity, something remarkable happens. The universe bounces back, triggering what we call the Big Bang, and starting the cycle all over again. This cyclic model solves one of the biggest problems with the traditional Big Bang theory. Instead of everything beginning from an impossible singularity, each cycle smooths out the wrinkles from the previous one. Think of it like a cosmic washing machine that cleans and resets the universe every few trillion years. The evidence for this comes from studying the cosmic microwave background radiation, the afterglow of the Big Bang that still fills all of space today. When scientists map this radiation in incredible detail, they find patterns that are almost too perfect to be explained by a single Big Bang event. The temperature variations are so precisely calibrated that it's like finding a perfectly shuffled deck of cards. But in a cyclic universe, this makes perfect sense. Each cycle acts like a cosmic filter, removing irregularities and creating the smooth, uniform conditions we observe today. Over countless cycles, the universe has had time to work out all the kinks and achieve the nearly perfect balance we see around us. The mathematics behind this is mind-bending. During the contraction phase, time itself starts running backwards from our perspective. Events that seem to happen in sequence during our expansion phase actually happened in reverse order during the previous contraction. It's as if the universe is playing the same cosmic movie forwards and backwards for all eternity. Recent observations of distant supernovas suggest that the expansion of our universe is actually accelerating, driven by something called dark energy. But in the cyclic model, this acceleration is temporary. Eventually, dark energy will weaken and gravity will take over, starting the next contraction phase. The timeline is staggering. Each complete cycle takes about 1 trillion years. We are currently about 14 billion years into the expansion phase, which means we have roughly 986 billion years to go before the universe starts contracting again. What's even more incredible is that information from previous cycles might survive the bounce. Some researchers think that complex structures like black holes or even patterns of matter could make it through the transition, carrying traces of ancient universes into our current cosmic era. If this theory is correct, then what we call the Big Bang was actually a cosmic collision between our contracting universe and something else entirely. The ekpyrotic scenario, cosmic collisions picture. Two vast sheets of space-time hurtling toward each other through a higher dimension that we can't see. When they collide, the impact creates our entire universe in a cosmic crash that makes the Big Bang look gentle. This is the ekpyrotic scenario, named after the ancient Greek word for conflagration. Instead of our universe beginning from a single point, it emerged from the collision between two three-dimensional spaces called branes, moving through a higher dimensional realm that exists beyond our everyday experience. Think of it like two enormous soap bubbles floating toward each other in a bathtub. When they touch, they don't just merge smoothly. They create ripples, waves, and disturbances that spread throughout both bubbles. Except in this case, the bubbles are entire universes, and the ripples become the matter and energy that fill all of space. The beauty of this model is that it explains why our universe is so remarkably flat and uniform. When the two branes collided, the impact smoothed out any irregularities that existed before, creating the nearly perfect cosmic conditions we observe today. It's like two rough wooden boards being pressed together so hard that both surfaces become perfectly smooth. But here's where it gets really strange. These colliding branes exist in what physicists call the bulk, a higher dimensional space that contains multiple universes, like bubbles in champagne. Our entire reality, everything we can see and touch and measure, is confined to the surface of one of these branes. We're essentially living in a three-dimensional slice of a much larger cosmic structure. The collision happened about 13.8 billion years ago, which explains why that's the age of our observable universe. But the brains themselves could be infinitely old, drifting through the bulk for eternity until the moment of impact that created our cosmic home. Scientists think they might be able to detect evidence of this collision by studying gravitational waves, ripples in space-time itself that travel at the speed of light. The impact between two brains would have created massive gravitational wave signatures that should still be detectable today, like echoes from the most powerful explosion in cosmic history. What's even more mind-bending is that the collision might not have been random. Some versions of the ekpyrotic theory suggest that the brains are attracted to each other by forces operating in the higher dimensional bulk. They're destined to collide repeatedly, creating universe after universe in an endless series of cosmic crashes. Each collision could create a universe with slightly different physical laws, different particles, different forces. Most of those universes would be sterile and lifeless. But occasionally, a collision would create conditions just right for stars, planets, and eventually life to emerge. The other brain that collided with ours might still exist now, moving away from us through the higher dimensional bulk. In a sense, we might have a cosmic twin, a parallel universe that was born in the same collision that created our reality. The mathematical models describing brain collisions are incredibly complex, involving equations that operate in 11 dimensions. Yet when physicists run computer simulations of these collisions, they find that the results match many of the features we observe in our universe. The timing of the collision, the energy released, and the resulting structure all align with what we see in the cosmic microwave background and the large-scale distribution of galaxies. But to understand how such collisions are possible, we need to explore the strange mathematics of extra dimensions. Loop, quantum gravity, space has pixels. What if space itself has a smallest possible size, like the pixels on a computer screen? This revolutionary idea suggests that when you zoom far enough into the fabric of reality, space stops being smooth and starts looking like a cosmic mesh made of tiny loops. Loop quantum gravity proposes that space is not infinitely divisible. Just like matter is made of atoms, space itself is constructed from fundamental building blocks called loops. These loops are so incredibly small that if you enlarged an atom to the size of the observable universe, a single loop would still be smaller than an atom. Think of space like a piece of fabric. From far away, it looks perfectly smooth. But get close enough with a powerful microscope, and you start to see the individual threads that weave it together. These quantum loops are the threads of space-time itself, twisted and knotted together in patterns so complex that they create the illusion of smooth, continuous space. This changes everything about what could have happened before the Big Bang. In loop quantum gravity, the density of matter can never become infinite because space itself has a minimum size. When the universe contracts during a big crunch, it can only squeeze down until the loops of space are pressed together as tightly as possible. At that point, space itself pushes back. It's like trying to compress a spring. The more you squeeze it, the harder it pushes back. When the universe reaches maximum compression, the quantum structure of space creates a repulsive force so powerful that it reverses the collapse and triggers what we call the Big Bang. But from this perspective, the Big Bang is really a big bounce. The numbers are staggering. At maximum compression, the universe would have a density of about 10 to the power of 96 kilograms per cubic meter. That's so dense that a single teaspoon would weigh more than all the matter in the observable universe today. Yet even at this incredible density, the quantum loops prevent a true singularity from forming. Recent computer simulations of loop quantum gravity show that the bounce happens smoothly without any infinite quantities or mathematical breakdowns. The universe contracts down to the minimum possible size, then immediately begins expanding again. The entire bounce process takes less than 10 to the negative 43rd power seconds. What makes this theory even more compelling is that it predicts specific signatures in the cosmic microwave background radiation that we might be able to detect. If our Big Bang was actually a bounce, it should have left characteristic patterns in the afterglow radiation that still fills the universe today. Scientists are using increasingly sophisticated telescopes to search for these bounce signatures. They're looking for tiny correlations in the temperature fluctuations of the cosmic microwave background that would indicate our universe emerged from a previous cosmic cycle. The European Space Agency's Planck satellite has already mapped the cosmic microwave background with unprecedented precision. When scientists analyze this data using loop quantum gravity models, they find tantalizing hints that our universe might indeed have bounced from a previous cycle. The implications are profound. If loop quantum gravity is correct, then the Big Bang was not the beginning of time, but just the most recent episode in an eternal cosmic drama. Our universe could be one of countless others that have bounced back from the brink of collapse. But this bouncing universe might be just one of many possible cosmic cycles operating in dimensions we can barely imagine. The death and rebirth cycle. The universe is dying right now, but don't panic. In the Big Bounce theory, cosmic death is just cosmic rebirth waiting to happen. Right now, our universe is expanding and cooling. Stars are burning through their fuel. Galaxies are drifting apart. In about 100 trillion years, the last star will flicker out, leaving behind a cold, dark cosmos filled with nothing but black holes and empty space. This is what physicists call the heat death of the universe. But the Big Bounce theory says this isn't the end of the story. It's just the end of the first act. As the universe continues to expand and cool, something extraordinary happens to the fundamental forces that hold reality together. Dark energy, the mysterious force currently accelerating cosmic expansion, begins to weaken. Think of dark energy like a stretched rubber band that's been holding the universe apart. As it weakens, gravity starts to win the cosmic tug of war. The expansion slows down, stops, and then reverses. The universe begins contracting, pulling everything back together in what scientists call the Big Crunch. But here's where the Big Bounce differs from a simple collapse. As the universe contracts, quantum effects that are normally too small to notice become incredibly important. The same quantum mechanics that prevents atoms from collapsing also prevents the universe from collapsing into a true singularity. During the contraction phase, space itself becomes compressed like a cosmic spring. Galaxies crash into each other. Stars merge and explode. Matter gets heated to incredible temperatures as everything in the universe gets squeezed into a smaller and smaller volume. The temperature rises to trillions of degrees, hot enough to break apart atomic nuclei and reduce all matter to its most fundamental components. As the compression continues, something remarkable happens. The quantum properties of space-time create a repulsive force that grows stronger as the universe gets smaller. It's like trying to squeeze a balloon filled with water. The more you compress it, the harder it pushes back. When the universe reaches its minimum possible size, about 10 to the negative 65th meters, the quantum repulsion becomes so powerful that it reverses the entire process. The Big Crunch becomes a Big Bang, and the universe explodes outward again in a fresh cycle of cosmic expansion. The entire bounce process happens incredibly quickly. The universe goes from maximum expansion to maximum contraction and back to expansion again in less than a cosmic second. From the perspective of someone living through it, the bounce would be instantaneous and probably undetectable. What's fascinating is that each bounce cycle could reset the physical laws of the universe. The forces that govern matter and energy might be slightly different in each cycle. Most cycles would create sterile universes where stars and planets couldn't form, but occasionally, the bounce would create conditions perfect for complexity and life. Scientists estimate that each complete cycle takes about 2 trillion years. We're currently about 14 billion years into an expansion phase, which means we have roughly 1.986 trillion years before the next bounce. During each cycle, the universe undergoes a complete transformation. The matter and energy that exist today will be completely recycled, reorganized, and redistributed in the next cycle. But some information from our current universe might survive the bounce. Complex patterns in the quantum vacuum, gravitational wave signatures, or even the fundamental structure of space-time itself might carry traces of our cosmic epoch into the next cycle. This raises profound questions about the nature of existence and consciousness. If our universe has gone through countless cycles before and will go through countless more after, what does this mean for our significance in the cosmic story? But the big bounce might be happening in dimensions we can't even see. String theory and hidden dimensions. Our universe has a secret hidden beyond the 3 dimensions of space that we experience every day. There might be 6 additional dimensions curled up so tightly that we can't detect them directly. String theory suggests that the fundamental building blocks of reality aren't particles at all, but tiny vibrating strings existing in a space with 9 dimensions plus time. These strings are so small that if an atom were enlarged to the size of the solar system, a string would still be smaller than a tree on Earth. Think of these extra dimensions like a garden hose viewed from far away. From a distance, the hose looks like a one-dimensional line. But get closer, and you realize it actually has width and depth. The extra dimensions of string theory are curled up in a similar way. Too small for us to perceive, but crucial for the mathematics of reality to work correctly. Before the Big Bang, these extra dimensions might have been large and accessible. Our familiar 3 dimensions of space could have been just a small subset of a much richer, more complex geometric structure. The Big Bang might have been the event that caused 6 of these dimensions to curl up and hide, leaving us trapped in the 3-dimensional slice we call home. But here's where it gets mind-bending. In the pre-Big Bang era, matter and energy could have moved freely through all 9 spatial dimensions. Imagine being able to step sideways out of our universe entirely, the way a 3-dimensional person can step out of a 2-dimensional drawing on paper. That's what motion through extra dimensions would be like. The shape of these hidden dimensions determines the fundamental forces and particles we observe in our universe. Different geometric configurations produce different types of matter. Different strengths of forces, different physical laws. It's like how the shape of a musical instrument determines what sounds it can make. The extra dimensions are the cosmic instrument, and the particles and forces we see are the music it plays. Recent calculations suggest that the transition from large extra dimensions to small curled up ones released enormous amounts of energy. This dimensional phase transition might have been what powered cosmic inflation, the rapid expansion that shaped our universe in its first moments. The mathematics is staggering. In 9 dimensions, there are millions of different ways to curl up the extra 6 dimensions into compact shapes. Each configuration represents a different possible universe with its own unique physics. Most of these configurations would create universes where atoms couldn't form or stars couldn't shine. We live in one of the rare configurations that allows complexity and life. But the other configurations might not be lost forever. Some string theorists think that cosmic events like black hole collisions or vacuum phase transitions could temporarily uncurl the extra dimensions, giving us brief glimpses into the larger geometric structure that exists beyond our three-dimensional prison. Scientists are designing experiments to search for evidence of extra dimensions by looking for particles that seem to disappear from our universe, only to reappear somewhere else. If extra dimensions exist, particles should be able to take shortcuts through higher dimensional space, allowing them to travel faster than light from our three-dimensional perspective. The Large Hadron Collider has been searching for signs of extra dimensions by looking for missing energy in particle collisions. When high-energy particles collide, some of the energy might escape into the extra dimensions, creating characteristic signatures that physicists can detect. So far, no definitive evidence of extra dimensions has been found, but the search continues with increasingly sensitive instruments and higher energy collisions. The implications are profound. If string theory is correct, the Big Bang wasn't the beginning of everything, but just the moment when our particular three-dimensional slice of a larger cosmic structure began its independent existence. But even this might be just one episode in an even grander cosmic story. Eternal inflation and the multiverse. Imagine a cosmic factory that never stops producing big bangs. Welcome to eternal inflation, where our universe is just one bubble in an infinite ocean of constantly expanding space. While our Big Bang happened 13.8 billion years ago, and inflation in our region ended almost immediately, inflation never actually stops everywhere. In the larger cosmic structure, space keeps inflating forever, occasionally spawning new universe bubbles like ours in an endless process that has no beginning and no end. Think of it like a pot of boiling water where bubbles constantly form and rise to the surface. Except in this case, each bubble is an entire universe with its own Big Bang, its own galaxies, its own potential for stars and planets and life. And the pot itself is infinite, so the bubble production never runs out of space or time. Our observable universe, everything we can see with our most powerful telescopes, represents just one tiny region inside one of these cosmic bubbles. Beyond the edge of what we can observe, our bubble universe continues expanding. And beyond that, there are other bubble universes, each one created by its own Big Bang event in the eternally inflating space. The scale is mind-boggling. If you could somehow travel faster than light and escape our cosmic bubble, you would find yourself in the inflating space between universes. From this perspective, you would see bubble universes scattered throughout space, like soap bubbles in a bathtub, each one appearing and evolving according to its own timeline. But here's the strangest part. In eternal inflation, every possible universe that can exist does exist. There are universes where the force of gravity is twice as strong as in ours. Universes where electrons have different masses. Universes where stars burn blue instead of yellow. Universes where the laws of physics are so different that matter as we know it cannot exist. The mathematics suggest that in infinite space, every possible arrangement of matter and energy will eventually occur. This means there are exact copies of our universe scattered throughout the infinite cosmic foam. There are universes almost identical to ours, but where you wore a different color shirt today. There are universes where dinosaurs never went extinct, where humans never evolved, where Earth never formed. Scientists think they might be able to detect evidence of other bubble universes by looking for collision signatures in our cosmic microwave background radiation. If our bubble universe ever bumped into another one, it would leave a characteristic pattern of hot and cold spots that we could potentially observe with sensitive enough telescopes. The Planck satellite has already found some anomalous patterns in the cosmic microwave background that some scientists interpret as potential evidence of bubble universe collisions. While these findings are still controversial, they represent one of the first possible observational clues about the existence of the multiverse. The eternal inflation scenario also explains why the physical constants in our universe seem so perfectly fine-tuned for life. In an infinite collection of universes with random physical laws, some will inevitably have the right conditions for complexity and consciousness to emerge. We exist in one of these rare life-friendly universes simply because we couldn't exist anywhere else. This is known as the anthropic principle, the idea that we observe the universe to be fine-tuned for life because we couldn't exist to observe any other type of universe. But eternal inflation raises profound questions about the nature of reality itself. If every possible universe exists, what makes our particular universe special? Are we just one random outcome in an infinite cosmic lottery? And if space is truly infinite, does anything we do really matter in the grand scheme of things? The answer might lie in an even stranger possibility than infinite universes. What if our entire universe exists inside a black hole, living inside a black hole? This isn't science fiction. It's a serious scientific theory that could explain some of the deepest mysteries about cosmic origins. When a massive star collapses to form a black hole, the mathematics suggests something remarkable happens. Instead of creating a simple point of infinite density, the collapse might create an entirely new region of space-time that expands rapidly, forming what appears to be a universe from the inside. Think of it like this. From our perspective outside a black hole, we see matter falling in and disappearing forever. But from the perspective of someone falling into the black hole, space itself starts expanding rapidly around them. What looks like a cosmic dead end from the outside becomes a cosmic birth from the inside. The numbers work out surprisingly well. A black hole with the mass of our observable universe would have an event horizon roughly the same size as our cosmic horizon, the edge of the region we can actually see. This isn't just a coincidence. It suggests there might be a deep connection between black holes and the structure of our cosmos. But here's where it gets really mind-bending. If our universe is inside a black hole, then that black hole exists in a larger parent universe. And that parent universe might itself be inside an even larger black hole. It's black holes all the way up, an infinite hierarchy of nested realities where each universe is contained within a black hole in the universe above it. This model naturally explains cosmic inflation. When the parent universe's star collapsed to form the black hole that contains us, the rapid compression triggered the explosive expansion we call the Big Bang. From our perspective inside the black hole, space inflated dramatically. From the parent universe's perspective, a new black hole simply formed according to the normal laws of physics. The theory also explains why our universe appears to be expanding faster and faster. As more matter falls into our parent black hole from the outside, it adds energy to our interior universe, accelerating the expansion we observe as dark energy. We're not just riding along in an expanding universe. We're being fed energy from a larger cosmic structure we can never directly observe. Recent computer simulations show that black hole interiors can indeed develop the kind of large-scale structure we see in our universe. Galaxies, galaxy clusters, and vast cosmic voids all emerge naturally from the gravitational dynamics inside a rotating black hole. What's even more fascinating is that every black hole in our universe might contain its own interior cosmos. The supermassive black hole at the center of our galaxy, weighing 4 million times more than our sun, could house an entire universe filled with its own galaxies, stars, and planets. From their perspective, they would see a cosmos that looks just as vast and ancient as ours does to us. This creates a stunning possibility. If intelligence and technology can develop inside black hole universes, they might eventually learn to create black holes of their own. Each new black hole would spawn another universe populated with its own potential for consciousness and creativity. Universes giving birth to universes. In an endless chain of cosmic reproduction, the implications extend beyond just cosmic structure. If we're living inside a black hole, then the information that describes our entire universe, every particle, every force, every pattern of matter and energy, exists on the two-dimensional surface of the black hole's event horizon. This leads us to one of the most radical ideas in modern physics: the possibility that reality itself might be a hologram. The holographic universe. But if our universe is inside a black hole, where does the information about our reality actually exist? Reality might be an illusion. Everything you think exists in three-dimensional space could actually be information encoded on a two-dimensional surface, like a cosmic hologram projecting the universe around us. The holographic principle emerged from studying black holes and the paradox of information. When matter falls into a black hole, it seems to disappear from our universe forever. But the laws of physics say that information cannot be destroyed. So where does the information about that fallen matter actually go? The answer changes everything we thought we knew about space and reality. The information doesn't fall into the black hole at all. Instead, it gets encoded on the black hole's event horizon, the two-dimensional surface that marks the point of no return. From our perspective outside the black hole, all the information about the fallen matter is preserved as patterns on this cosmic boundary. Think of it like a shadow puppet show. The three-dimensional puppets behind the screen create two-dimensional shadows that contain all the information about their shapes and movements. In the holographic universe, we might be like those shadows. Three-dimensional beings whose entire existence is actually encoded as information on a distant two-dimensional boundary. Recent mathematical breakthroughs suggest that our entire observable universe might work this way. All the information about every galaxy, every star, every planet, and every person could be encoded on a two-dimensional surface at the very edge of space. What we experience as three-dimensional reality is actually a holographic projection from this cosmic boundary. The implications are staggering. This means that the amount of information in any region of space is not determined by its volume, but by the area of its boundary. A sphere twice as wide doesn't contain 8 times as much information as you might expect from its volume. It contains only 4 times as much, proportional to the increase in its surface area. This principle might explain what happened before the Big Bang. If our universe is a holographic projection, then the Big Bang wasn't the beginning of space and time, but the moment when information encoded on a cosmic boundary began projecting our three-dimensional reality. The before exists as pure information on the holographic surface, outside of space and time as we understand them. Scientists are searching for evidence of the holographic principle by looking for pixelation in space itself. If space is ultimately two-dimensional, then at the smallest scales, we should detect a fundamental graininess where the holographic projection becomes apparent. Experiments using laser interferometers are pushing the boundaries of measurement precision to search for these cosmic pixels. The idea is that if space has a finite information content, There should be a minimum distance scale, below which no additional information can be stored. Some researchers have proposed that the quantum foam we discussed earlier might actually be a manifestation of this holographic pixelation. The bubbling and churning at the smallest scales of space might be the result of information processing on the cosmic boundary. The holographic principle also suggests that black holes in our universe are not actually three-dimensional objects, but two-dimensional information storage systems that appear three-dimensional from our perspective. When a black hole evaporates through Hawking radiation, it's actually returning stored information back to the holographic boundary that creates our reality. This creates a remarkable picture. Black holes as cosmic hard drives, storing and processing information on their event horizons, while appearing to be three-dimensional objects from our perspective inside the hologram. But if reality is holographic, how did the information get encoded on the boundary in the first place? The answer might involve quantum processes that can create universes spontaneously from pure nothingness. Quantum creation from nothing. Nothing can become something. In the quantum world, universes can literally tunnel into existence from absolute nothingness. And this might be exactly how our cosmos began. Quantum tunneling is one of the strangest phenomena in physics. It allows particles to pass through barriers that should be impossible to cross, like a ball rolling through a solid wall instead of bouncing off it. This happens because at the quantum level, particles don't have definite positions. They exist as probability clouds that can extend through seemingly impenetrable barriers. Now imagine applying this principle to the universe itself. Before the Big Bang, there was no space, no time, no matter, no energy. There was literally nothing. But in quantum mechanics, even nothing is something. The quantum vacuum is filled with virtual particles, popping in and out of existence, energy fluctuations, and probability waves that can occasionally produce real, measurable effects. In this quantum nothingness, there's a tiny but non-zero probability that a universe could tunnel into existence spontaneously. Think of it like a cosmic lottery, where the winning ticket is the sudden appearance of space, time, and all the energy needed to create everything we see around us. The mathematics shows that a quantum universe would start incredibly small, smaller than a proton, and immediately begin inflating through the process we call cosmic inflation. Within a fraction of a second, this microscopic quantum fluctuation becomes a universe large enough to contain billions of galaxies. But here's what makes this theory so compelling. The universe that tunnels into existence from nothing would naturally have exactly zero total energy. All the positive energy in matter and radiation would be perfectly balanced by the negative energy in gravitational fields. It's like a cosmic accounting system, where every debit has a corresponding credit, allowing the universe to exist without violating conservation of energy. This solves one of the biggest puzzles about cosmic origins: how something can come from nothing without violating the fundamental laws of physics. The probability of quantum tunneling creating a universe is incredibly small, roughly 1 chance in 10 to the power of 10 to the 120th. That's a number so tiny that if you wrote it out, it would have more zeros than there are atoms in the observable universe. But in an eternal quantum vacuum, even impossibly rare events will eventually happen. What's even more remarkable is that this process might be happening constantly. Virtual universes could be tunneling into existence throughout the quantum vacuum, most of them collapsing back into nothingness almost immediately. Only occasionally would a universe like ours successfully inflate and evolve into something complex and long-lasting. Recent experiments in quantum mechanics have demonstrated tunneling on increasingly large scales. Scientists have observed tunneling in systems containing thousands of atoms, suggesting that the principle might indeed apply to macroscopic objects like entire universes. In 2019, researchers at the University of California demonstrated quantum tunneling in a system of about 1,000 atoms, showing that the effect can occur in relatively large quantum systems. While this is still far from universe-sized, it suggests that quantum tunneling might scale up to cosmic proportions. The quantum tunneling origin also explains why our universe has the particular properties it does. Different universes would tunnel into existence with different physical constants, different numbers of dimensions, different fundamental forces. We exist in a universe whose properties allow for complexity and consciousness, simply because we couldn't exist in any other type. But if universes can tunnel into existence from nothing, there might be an infinite number of them doing exactly that. This brings us to perhaps the most mind-bending implication of all: the multiverse. The multiverse and our place in it. We are not alone. Our universe might be just one of infinitely many realities existing simultaneously in a vast cosmic multiverse. And what happened before our Big Bang might be happening right now in countless other cosmic domains. The multiverse isn't a single theory, but a consequence of several different areas of modern physics, all pointing toward the same stunning conclusion. Whether you follow the mathematics of eternal inflation, string theory, quantum mechanics, or cosmic evolution, you arrive at the same place. Reality is far larger and stranger than anything contained within our observable universe. Think of it like a cosmic archipelago, where each island is an entire universe. Some islands are close enough to occasionally interact with each other. Others are so distant that they exist in complete isolation. And new islands are constantly forming through processes we're only beginning to understand. In the quantum multiverse, every possible outcome of every quantum event creates a new branch of reality. When a particle can be in two different states, both states actually occur, but in parallel universes. This means there are versions of reality where every historical event played out differently, where every person made different choices, where evolution took entirely different paths. In the many worlds interpretation of quantum mechanics, every time a quantum measurement occurs, the universe splits into multiple branches. Right now, as you read these words, countless versions of you are reading slightly different versions of this script in parallel realities. The inflationary multiverse suggests that cosmic inflation creates new universe, bubbles constantly. Each bubble has its own Big Bang, its own physical laws, its own potential for complexity and life. Our universe is just one bubble in an infinite cosmic foam, where new realities are being born every moment. String theory adds another layer by proposing that different configurations of extra dimensions create universes with completely different physics. There might be universes where atoms can't form, where stars can't shine, where the forces are too weak or too strong to allow anything interesting to happen. But here's the mind-bending connection to what came before our Big Bang. In an infinite multiverse, the distinction between before and after becomes meaningless. Events that we think of as preceding our universe might actually be happening simultaneously in parallel realities. The processes that led to our Big Bang could be ongoing right now in other parts of the multiverse. Recent observations of the cosmic microwave background radiation show patterns that some scientists interpret as evidence of collision marks from other universes. If our universe bubble bumped into another one during its early expansion, it would leave characteristic signatures that we might be able to detect with sufficiently sensitive instruments. The cold spot in the cosmic microwave background, a region that's significantly colder than the surrounding area, might be evidence of such a collision. While alternative explanations exist, the possibility that it represents a scar from an encounter with another universe remains tantalizingly open. The mathematics suggests that in an infinite multiverse, every possible universe exists, including exact duplicates of our own. There are versions of you reading these words in universes almost identical to ours. There are versions where dinosaurs never went extinct, where different species became intelligent, where Earth never formed at all. This raises profound questions about identity, meaning, and the nature of existence itself. If every possible version of reality exists somewhere in the multiverse, what makes our particular branch special? Are we just one random outcome among infinitely many possibilities? But the multiverse also offers hope. If our universe is part of a larger structure, then the death of our cosmos doesn't mean the end of everything. Other universes would continue evolving, creating new possibilities for consciousness and experience to emerge in forms we can barely imagine. The connection between our universe and the multiverse might be deeper than we think. Perhaps consciousness itself is what allows us to experience one particular branch of infinite reality, making us not just observers of the cosmos, but active participants in determining which version of the multiverse becomes real. This leads us to one of the most profound questions in all of science. What role does consciousness play in creating reality? The role of consciousness. What if consciousness doesn't just observe the universe, but actually helps determine which version of reality becomes real? This isn't mystical speculation. It's one of the most profound puzzles in quantum mechanics. And it might hold the key to understanding not just what came before the Big Bang, but why we exist in this particular universe instead of any of the countless alternatives. In quantum mechanics, particles exist in multiple states simultaneously until they are observed. The famous double-slit experiment shows that a photon can travel through two different paths at the same time, creating an interference pattern that proves both paths were taken. But the moment you try to measure which path the photon actually took, the superposition collapses and the photon is found to have taken only one path. This is called the measurement problem. And after a century of debate, physicists still don't agree on what causes quantum collapse. Some think it's a fundamental property of nature. Others believe it's caused by interaction with the environment. But a growing number of scientists think consciousness itself might play a crucial role. If consciousness is required to collapse quantum states, then the emergence of consciousness in our universe might have retroactively determined which version of cosmic history became real. Before intelligent life evolved, our universe might have existed in a superposition of all possible histories simultaneously. The development of consciousness selected one specific timeline from the quantum multiverse. Think of it like a cosmic, choose-your-own-adventure story, where all possible plot lines exist simultaneously until someone reads the book. The act of reading collapses the superposition and selects one particular story from all the possibilities. Consciousness might be the cosmic reader that determines which version of reality gets experienced. This connects directly to the mystery of cosmic fine-tuning. Our universe seems perfectly calibrated for the emergence of complexity and consciousness. Maybe that's not a coincidence. Maybe consciousness retroactively selected the cosmic parameters that would allow it to exist in the first place. In the many worlds interpretation of quantum mechanics, all possible universes exist simultaneously in parallel realities. Consciousness doesn't collapse the wave function, but rather selects which branch of the multiverse gets experienced subjectively. From this perspective, versions of you exist in universes with different cosmic parameters, different histories, different physical laws. Recent experiments in quantum biology suggest that consciousness might indeed have special quantum properties. The quantum processes in microtubules inside neurons, the quantum effects in photosynthesis, and the quantum nature of smell and possibly even memory suggest that consciousness operates at the intersection between the quantum and classical worlds. If consciousness has quantum properties, it might be able to access information from parallel realities through quantum entanglement. Intuition, creativity, and even déjà vu might be glimpses of alternate timelines where events unfolded differently. But the most radical possibility is that consciousness might be fundamental to reality itself, not just an emergent property of complex information processing. Some theories suggest that consciousness is woven into the basic structure of spacetime, making it a cosmic force as fundamental as gravity or electromagnetism. If consciousness is fundamental, then it might have existed even before the Big Bang, in whatever pre-cosmic state gave birth to our universe. The development of conscious life in our cosmos might be the universe becoming aware of itself, completing a cosmic feedback loop that began before space and time existed. This idea is supported by the integrated information theory of consciousness, which suggests that consciousness arises whenever information is integrated in complex ways. If this is true, then consciousness might be a basic feature of any sufficiently complex system, including the universe itself. But if consciousness is fundamental to reality, maybe reality itself is more like mathematics than physics, the mathematical universe. What if our universe isn't made of matter and energy at all, but is pure mathematics expressing itself as physical reality? This radical idea suggests that what we call physical reality is actually mathematical relationships playing out according to logical rules. Every particle, every force, every law of physics would be mathematical entities existing in a vast computational space that we experience as the universe around us. Think of it like a video game where the characters inside believe their world is made of real objects. From their perspective, the sword feels solid, the fire feels hot, and the gravity feels real. But from outside the game, we know that everything is just mathematics running on a computer processor. Our universe might be the ultimate version of this computational reality. The mathematical universe hypothesis explains why mathematics is so unreasonably effective at describing physical reality. Instead of asking why math works so well to describe the universe, we should ask why we're surprised that mathematical relationships follow mathematical rules. If reality is mathematics, then the effectiveness of math is simply logical. This perspective radically changes what it means to ask what came before the Big Bang. Mathematical relationships don't begin or end the way physical objects do. They simply exist in the space of all possible mathematical structures. Our Big Bang might have been the moment when one particular mathematical structure began computing itself into existence. Consider the number pi. It contains infinite information about circles, geometry, and mathematical relationships. But pi doesn't exist somewhere in space or sometime in history. It exists in the abstract realm of mathematical truth. If our universe is mathematical, it might exist in a similar way as a self-computing mathematical structure in the space of all possible computations. Recent advances in computational cosmology support this view. When scientists simulate universe formation on supercomputers, they find that simple mathematical rules can generate incredibly complex cosmic structures. Galaxies, galaxy clusters, and vast cosmic voids all emerge naturally from basic equations describing gravity and thermodynamics. But here's where it gets really strange. But here's where it gets really strange. If reality is mathematical, then every possible mathematical structure might correspond to some real universe. There would be universes based on different geometries, different algebras, different logical systems. Most of these mathematical universes would be too simple or too chaotic to support complexity, but some would develop rich structures capable of supporting mathematics-based consciousness. The computational universe hypothesis suggests that consciousness itself might be a mathematical process running on the substrate of space-time. Our brains would be biological computers implementing mathematical algorithms that create the subjective experience of being aware. Thoughts, emotions, and perceptions would all be mathematical operations in the cosmic computation. This explains why we find mathematical beauty in nature. Mathematical consciousness recognizes mathematical structure because they are fundamentally the same type of entity. The elegance we perceive in equations isn't aesthetic but logical recognition of mathematical truth expressing itself. If our universe is mathematical, then what came before the Big Bang was not a physical state, but a mathematical precondition. The universe might have emerged when mathematical self-consistency requirements selected our particular cosmic algorithm from the space of all possible computations. Advanced computer simulations are testing this idea by seeing how much of cosmic evolution can be reproduced using pure mathematical rules with no reference to physical substance underneath. The results suggest that mathematics alone might be sufficient to generate everything we observe as physical reality. But mathematical universes might undergo transitions that look very different from physical cosmic evolution. Our universe might be living in a false paradise that could collapse at any moment, revealing the true cosmic reality that lies beneath our apparent stability. Vacuum decay. Living on the edge. In particle physics, what we call empty space isn't actually empty. It's filled with quantum fields that permeate every cubic inch of the universe. These fields have energy states, and our universe exists in what might be a local minimum of energy, rather than the true ground state. It's like living on a high plateau that feels stable, but could suddenly give way to a much deeper valley. Think of the vacuum state like a ball sitting in a shallow depression on a hillside. The ball seems stable and secure in its little valley. But if something gives it a small push, it might roll out of the depression and tumble down to a much lower position on the hill. Our universe might be that ball, sitting in a cosmic valley that looks stable but isn't the deepest possible state. If vacuum decay occurs, it would happen through quantum tunneling. Somewhere in the universe, a small bubble of true vacuum would spontaneously appear, expanding at the speed of light and converting everything it touches to a lower energy state. The physical laws inside this bubble would be completely different from ours. Atoms might not be able to form. The forces might be too weak or too strong to allow any kind of complex structure. But here's the connection to what came before the Big Bang. If our universe exists in a false vacuum state, then what we call the Big Bang might have been a vacuum decay event from a previous cosmic configuration. Our entire reality might be the interior of an expanding bubble that formed through vacuum decay in some larger, more fundamental cosmic structure. Recent calculations suggest that the Higgs field, which gives mass to all particles, might be in exactly this kind of metastable state. The discovered mass of the Higgs boson puts our universe right on the edge between stability and instability. We're living in a cosmic zone where vacuum decay is possible, but not inevitable. The timeline for vacuum decay is terrifying and comforting at the same time. If it happens, we would never see it coming. The bubble wall would travel at the speed of light, so there would be no warning. But the probability of vacuum decay happening in any given year is so incredibly small that the universe would likely survive for far longer than its current age before such an event occurred. What makes this even more mind-bending is that vacuum decay might be happening constantly throughout the larger cosmic structure. If eternal inflation creates infinite space, then every possible quantum event, including vacuum decay, happens infinitely often. There might be vacuum decay bubbles expanding throughout the cosmic foam, each one creating a new type of reality with different physical laws. Some theories suggest that vacuum decay is how new universes are born. When a bubble of true vacuum forms, the energy difference between the false and true vacuum states drives a period of inflation inside the bubble, creating a new expanding cosmos with its own Big Bang. Our universe might be the interior of such a vacuum decay bubble. The most speculative possibility is that advanced civilizations might be able to trigger vacuum decay deliberately, either accidentally through high-energy physics experiments or intentionally as a way to escape a dying universe. If consciousness can influence quantum processes, then sufficiently advanced beings might be able to induce vacuum transitions that create new cosmic domains. But vacuum decay might be just one way that universes can evolve and reproduce. Cosmic natural selection universes might evolve, reproduce, and compete for survival just like living organisms, with our cosmos being the offspring of successful parent universes that came before. This isn't metaphor. It's a serious scientific theory that applies the principles of Darwinian evolution to the cosmos itself. If universes can reproduce, and if their offspring inherit modified versions of their physical laws, then cosmic evolution would naturally select for universes that are good at making more universes. Think of black holes as cosmic reproductive organs. When a black hole forms, some theories suggest it creates a new universe on the other side of its event horizon. The physical constants in this baby universe would be similar to, but slightly different from the parent universe. Just like biological offspring resemble but aren't identical to their parents. Universes that produce lots of black holes would have lots of offspring. Universes that produce few black holes would have few offspring. Over countless cosmic generations, the multiverse would become dominated by universes optimized for black hole production. This could explain why our universe seems fine-tuned for star formation, since stars are the factories that create black holes. The theory makes testable predictions. If cosmic natural selection is real, our universe should have physical constants that maximize black hole production. Recent calculations suggest this might actually be the case. The strength of gravity, the masses of particles, and the expansion rate of our universe all seem optimized to create the maximum possible number of black holes. But cosmic evolution might operate through mechanisms more sophisticated than simple black hole reproduction. If consciousness can influence quantum processes, then intelligent life might play a role in cosmic reproduction. Advanced civilizations might learn to create new universes deliberately, passing on their knowledge and values to their cosmic offspring. This would explain the apparent fine-tuning of our universe for consciousness and complexity. Universes that support intelligent life would be more likely to reproduce through the technological activities of their inhabitants. Sterile universes that couldn't support consciousness would be evolutionary dead ends. The timeline for cosmic evolution is staggering. If each universe generation lasts about 100 trillion years, then our cosmos might be the product of billions of generations of cosmic evolution. The Big Bang that created our universe might have been just the latest birth in an ancient cosmic lineage, stretching back through time periods that make our 13.8 billion year history look like a brief moment. Different types of cosmic reproduction might create different evolutionary pressures. Universes that reproduce through vacuum decay would evolve differently from universes that reproduce through black hole formation. Universes that reproduce through conscious intervention would evolve in yet another direction. The most speculative possibility is that cosmic natural selection might eventually produce universes capable of reproducing across different dimensions or different mathematical frameworks. Advanced cosmic lineages might learn to create offspring universes with entirely different types of physics, exploring new regions of the space of all possible realities. If cosmic natural selection is real, then what came before our Big Bang was the reproductive act of a parent universe passing on its cosmic DNA to create us. We might be part of an evolutionary process that has been running for far longer than we can imagine, with our universe representing just one small branch on a vast cosmic tree of life. But if universes can evolve and reproduce, maybe they can also be artificially created. Are we living in a simulation? What if our entire reality is a simulation running on a cosmic computer, and what we call the Big Bang was simply the moment when someone pressed the start button? This isn't idle speculation anymore. As our own computing power grows exponentially, we're beginning to run sophisticated simulations of cosmic evolution. Advanced civilizations with vastly more computing resources could potentially simulate entire universes, with conscious beings who believe their reality is fundamental rather than computed. The mathematics are startling. A civilization just a few hundred years more advanced than us could have computing power sufficient to simulate the entire history of our observable universe in complete detail. They could run millions of such simulations simultaneously, creating vast populations of simulated beings who would have no way to detect that their reality was artificial. Think of how video game worlds have become increasingly realistic over just the past few decades. Characters in modern games exhibit complex behaviors and exist in detailed environments that follow consistent physical laws. Now imagine this technology advancing for thousands or millions of years. Eventually, the simulated beings might become conscious and begin asking questions about their cosmic origins. Recent work in computational cosmology shows that you don't need to simulate every particle in a universe to create conscious observers. You only need to simulate the specific regions and time periods that conscious beings actually observe. It's like a video game that only renders the parts of the world that players are currently looking at. This suggests that our universe might be computed on demand, rather than existing as a complete pre-calculated structure. When we look at distant galaxies through telescopes, the computer running our simulation might generate those galaxies in real time, creating a perfectly consistent cosmic history that extends as far back as we're capable of observing. The Big Bang itself might have been the initialization moment when the simulation began running. Instead of asking what came before the Big Bang, we should ask what motivated someone to start running a universe simulation in the first place. Were they trying to understand their own cosmic origins? Were they creating entertainment? Were they preserving the consciousness of beings from their own universe? Some versions of the simulation hypothesis suggest that we might be digital copies of real beings who lived in the original non-simulated universe. Our entire cosmic history might be a recreation of events that actually happened, run by future civilizations trying to understand or preserve their past. Advanced physics experiments might be able to detect evidence of computational limits in our universe. If reality is simulated, it must be running on finite computing resources, which would create subtle inconsistencies at the edges of what the simulation can handle. High-energy particle physics experiments might reveal pixelation effects or rounding errors that betray the digital nature of reality. The simulation hypothesis also explains the fine-tuning of our universe. If we're living in a simulation, our physical constants were programmed to allow complexity and consciousness to emerge. The programmers wouldn't waste computing resources on a boring universe where nothing interesting happens. But the most mind-bending possibility is that simulated beings might eventually develop the technology to run simulations of their own. We might be living in a nested hierarchy of simulations, with each level creating the level below it. The real universe at the top of this hierarchy might be so far removed from our experience that its nature is completely incomprehensible to us. If we are simulated beings, then the question of what came before our Big Bang becomes a question about the motivations and capabilities of our programmers. Testing the theories. All these wild theories about what came before the Big Bang aren't just philosophical speculation. They make specific predictions that we can test with real experiments and observations happening right now. Science advances by making predictions that can be proven wrong. The most exotic pre-Big Bang theories are only valuable if they tell us what to look for in the actual universe around us. And remarkably, many of these theories predict observable signatures that our current and planned instruments might be able to detect. Gravitational wave detectors are already online and getting more sensitive every year. The LIGO and Virgo observatories have detected dozens of black hole mergers and neutron star collisions. But the next generation of space-based gravitational wave telescopes will be sensitive enough to detect the primordial gravitational wave background from whatever cosmic event preceded our Big Bang. Different pre-Big Bang theories predict different gravitational wave signatures. A bouncing universe would create waves with specific frequency patterns related to the cosmic compression and expansion cycles. Colliding branes would produce characteristic polarization signatures. A universe emerging from quantum tunneling would generate waves with particular spectral properties. The Laser Interferometer, space antenna, LISA, planned for launch in the 2030s, will have arms millions of miles long and will be sensitive enough to detect gravitational waves from the first moments after the Big Bang. The cosmic microwave background radiation offers another window into pre-Big Bang physics. Satellite missions like Planck have already mapped this ancient light in extraordinary detail, revealing temperature fluctuations that encode information about the early universe. Future missions will measure polarization patterns with unprecedented precision, potentially revealing signatures of pre-inflationary physics. Scientists are specifically looking for non-Gaussianity in the cosmic microwave background, patterns that are too organized to be explained by simple quantum fluctuations during inflation. These signatures could indicate that our universe inherited structure from whatever came before the Big Bang. The European Space Agency is planning the Lightbird mission, which will search for primordial B-mode polarization in the cosmic microwave background. This would be a direct signature of gravitational waves from the inflationary epoch. Particle physics experiments at the Large Hadron Collider and future accelerators are probing the fundamental structure of matter and energy. If our universe exists in a false vacuum state, high-energy collisions might reveal the instability that could lead to vacuum decay. If extra dimensions exist, particle experiments might detect their signatures through missing energy or unexpected particle behaviors. The proposed Future Circular Collider would have 7 times the energy of the LHC and could probe physics at scales where extra dimensions become accessible. Astronomical observations are mapping the large-scale structure of the universe with incredible precision. The distribution of galaxies, the properties of dark matter, and the behavior of dark energy all contain information about cosmic origins. If our universe is part of a larger multiverse structure, we might detect signs of interactions with other cosmic domains. The James Webb Space Telescope is already looking deeper into space and further back in time than ever before. It's seeing galaxies that formed when the universe was very young, potentially revealing information about conditions that preceded normal cosmic evolution. The upcoming extremely large telescope will have a mirror 39 meters across and will be able to directly image potentially habitable planets around nearby stars. Laboratory experiments in quantum mechanics are testing the fundamental principles that govern reality at the smallest scales. Quantum entanglement experiments might reveal non-local correlations that extend beyond our universe. Quantum information experiments might detect computational limits that suggest we're living in a simulation. The most exciting possibility is that multiple lines of evidence might converge on the same pre-Big Bang theory. If gravitational wave detectors, cosmic microwave background observations, particle physics experiments, and astronomical surveys all point toward the same conclusion, we would have strong evidence for what actually happened before our universe began. But regardless of which theory turns out to be correct, the implications for humanity would be profound. What this means for us: we are not who we thought we were. The emerging picture of what came before the Big Bang changes everything about our place in the cosmic story and our destiny as a species. If our universe is part of an eternal cosmic cycle, then we are not living at the beginning of everything, but somewhere in the middle of an infinite story that has been unfolding for eternity. Our brief existence on this small planet represents just one moment in a cosmic drama that has played out countless times before and will continue long after our sun burns out. This should be humbling, but it's also empowering. If consciousness and intelligence have emerged before in previous cosmic cycles, then what we achieve as a species might not be lost forever when our universe eventually dies. The patterns of complexity and awareness that we represent might be preserved and carried forward into future cosmic epochs. If our universe emerged from the collision of higher dimensional brains, then we are living in the debris of a cosmic crash that happened in dimensions we can barely imagine. Our entire reality is the aftermath of an accident in a larger space that contains realities we could never directly experience. Yet somehow, this cosmic catastrophe created conditions perfect for life and consciousness to emerge. If we're living inside a black hole, then every black hole we observe might contain its own universe, complete with galaxies, stars, planets, and potentially life. This means the cosmos is far more alive and complex than we ever imagined, with consciousness emerging at scales and in locations we're only beginning to understand. If our universe is a holographic projection from a two-dimensional boundary, then everything we think of as real is actually information processing on a cosmic scale. This suggests that consciousness itself might be a fundamental feature of how information organizes itself into complex patterns. We're not just observers of reality, we're active participants in the cosmic computation that creates existence itself. The most radical possibility is that consciousness plays a fundamental role in determining which version of reality becomes real. If the multiverse contains all possible histories simultaneously, then the emergence of awareness might be what selects our particular cosmic timeline from infinite alternatives. This would make consciousness not just a product of cosmic evolution, but a participant in cosmic creation itself. As we develop more advanced technology, we might gain the ability to detect and even interact with these larger cosmic structures. Future civilizations might learn to communicate across universe boundaries, to travel through extra dimensions, or even to create new universes of their own. Humanity could evolve from a planetary species to a cosmic force capable of participating in the deepest levels of reality. But even if we never gain such cosmic abilities, understanding our true cosmic context changes how we think about meaning and purpose. We are not isolated accidents in a hostile universe. We are part of a vast, ancient, and ongoing cosmic story where consciousness and complexity play fundamental roles. The universe that gave birth to us was itself born from something greater. And what we create through our science, our art, our relationships, and our dreams becomes part of the cosmic inheritance that will influence whatever comes next. The endless story. In a very real sense, we are the universe becoming aware of its own infinite creative potential. The Big Bang was not the beginning. It was a transition. And we are not the end result of cosmic evolution. We are participants in a story that has no beginning and no end, only endless transformation and discovery. What happens next depends not just on the laws of physics, but on what we choose to do with the brief moment of consciousness we've been given in this vast cosmic tree. Every choice we make, every discovery we achieve, every act of creativity and compassion ripples outward into the cosmic structure that contains us. We are not just observers of this grand story. We are authors of it. The multiverse might contain infinite possibilities, but the particular branch of reality we experience is shaped by our actions, our decisions, our dreams, and our determination to understand our place in the larger cosmic symphony. Whether we live in a bouncing universe, a holographic projection, a mathematical computation, or a cosmic simulation, one thing remains constant. Consciousness has emerged in this corner of reality, and with it comes the responsibility to make our brief existence meaningful. The questions we've explored today: what came before the Big Bang, how reality is structured, whether we're alone in the multiverse, these aren't just abstract puzzles for physicists to solve. They're fundamental questions about who we are, where we came from, and what our purpose might be in the grand scheme of existence. As we push the boundaries of science and technology, as we build more sensitive instruments and develop more sophisticated theories, we're not just learning about the universe, we're participating in its evolution. Every telescope we point at the sky, every particle accelerator we build, every quantum experiment we perform is the universe using conscious beings like us to understand itself more deeply. We are the cosmos, investigating its own origins, its own structure, its own ultimate destiny. And in that investigation, we become more than just temporary arrangements of atoms and energy. We become active participants in the ongoing creation of reality itself. The story of what came before the Big Bang is ultimately the story of what we might become. It's a reminder that the universe is far stranger, far more wonderful, and far more full of possibility than we ever dared imagine. Final thoughts. If this journey through the deepest mysteries of existence has expanded your mind, make sure to subscribe to Stellify Science and hit that notification bell. We're just getting started, exploring the infinite wonders that surround us. Remember, every time you look up at the night sky, you're not just seeing distant stars and galaxies. You're looking at the visible edge of a reality that might extend infinitely beyond what we can observe. You're seeing the afterglow of events that might stretch back through cosmic cycles, through dimensional collisions, through quantum tunneling from nothingness itself. And you're doing it with a brain made of atoms forged in the hearts of ancient stars, in a universe that might be just one bubble in an infinite cosmic foam, possibly living inside a black hole in apparent reality, we'll never directly experience. The fact that you exist to contemplate these possibilities is perhaps the most extraordinary miracle of all. You're not just watching the universe, you're part of it, becoming aware of itself. Thanks for joining me on this incredible journey through the deepest mysteries of cosmic origins. Until next time, keep looking up, and remember that the biggest questions often have the most amazing answers. The universe is not only stranger than we imagine, it's stranger than we can imagine, and we're just getting started.